Okay, we've been looking at all different types of continuous distributions. And the question I get most often is, how do you know which type of distribution to follow and what formulas to use? The best way to deal with this is the central limit theorem. The central limit theorem tells us that no matter what the original distribution is, as long as we have a sample size larger than 30, typically the distribution is normally distributed. So we can use the central limit theorem to say that, the mean of the population is one thing, our mean has to be really close to that mean of the entire population. We can also say that the standard deviation is the standard error between our sample and the entire population. So the standard error of the mean is the description of how far on average the sample mean will be from the population mean. We're going to do a couple of examples. I'm going to show you how, again, that we can standardize or find the z-value of a given x value in a distribution and then find that probability based on the normal distribution. So the number of burgers made per minute at Good Burger averages mu of x, which is equal to 2.7 burgers, with a standard deviation of sigma of x being 0.64 of a burger. Consider the average number of burgers made over n equals 35 minutes during a day. Louise is collecting data at his local Good Burger. Determine the following. Okay, so here we have a sample, right? Louise is running his own sample. He is testing his Good Burger at n equals 35 intervals. The average for the national Good Burger chain here, the population of Good Burgers is 2.7. And the population standard deviation is about 64 of a burger. So 2.7, give or take a half a burger a minute. But if we want to know our sample here, of our sample, that we didn't have to take our population standard deviation because this is, if you look at the notation, the difference here is the bar on the x. Our sample error, which this is going to be divided by our n, which is 35 minutes. So we can see that we have a small error of 0.1 of a burger. What is the probability that Louise will get a sample mean higher than that of the true mean? So what's the probability that his mean is greater than 2.7 is what the question is asking. Well, if I was going to draw a sketch, we have our normal curve. I forgot my Post-its again, but that's okay. We need to know where 2.7 is on our normal curve here. So we have to find our z-value. So to find the z-value, I can do that z is equal to x bar minus mu over sigma divided by the square root of n. So this is our standard error here at the bottom. Okay, so our x bar is 2.7. The mean of the thing is 2.7 of the population, sorry. Divided by 0.108. When we get our z-score is 0. So we are right here on the mean. So we want to know what the chance is that the population is bigger than the average. So this is the area if I needed to find that information. Okay. Using the empirical rule, 50% of the data is above and below the mean, so that we can say that This is approximately 50%. Now that doesn't give us a lot of information. You could have done that intuitively. You could also not do it this way, by the way. You can go ahead and put that information into your calculator. That would be a normal CDF of our lower bound being 2.7 and our upper bound being infinity. For that, you just like type in 9 times 10 to the 9999th power, and then put in our standard error 0.1081, and it'll give you that same 50% answer. Anyways, that doesn't tell us a lot of information. That just tells us we have a 50% chance of getting a mean that's higher than the true mean. So what we'd like to do then is narrow that down. So in this next question, we're narrowing that down, and it says, what is the probability that we'll get a sample mean within 0.05 of the actual mean? So we're looking at a probability, if we look at our same normal curve here, that we are within 0.05 of the mean. So we want to see how close we can get, our local good burger can get to the population of good burgers. So that would be 2.65 and 2.75. Now, we can standardize that and get their z-value. I should have left myself some more space, but I'm going to go ahead and work that z-score right down here, or that z-value right here. Okay, so I'm going to start with 2.65, so that gives me x bars 2.65 minus mu of 2.7 divided by my 0.108 of my standard error. Okay, that gives me approximately negative 0.462. If I work the same with my other number, my 2.75, I should get, because the normal distribution is, sorry, hang on, let me write this so you can see where I'm going. The normal distribution is symmetrical. I should get the same answer, but I can set it up for you and you can rerun it for yourself. 2.75 minus 2.7 divided by 0.108. We have the same difference on the top, so we get a positive difference actually of 0.462. Okay, now I have been showing you how to do this with the technology. You can do this in Excel, in your calculator, either the TI-84 or the Inspire. I've been holding off on the tables because people either love them or hate them. So I'm going to show you how to use the tables, but keep in mind you can do this information with your calculator. You do not have to do it this way if you do not like it. So of these two numbers, I'm pulling up table E off of our resource page. It's the cumulative standard normal distribution. So we're looking for negative 0.4 on the left side. You have to go all the way over here, negative 0.4, and then we're looking for the 6 on the top, and then we'll find the number, and this is going to give us the area, if you need to see a picture, below our z-score. So we're going to find, on the table, we're going to find the area below this z-score and the area below this z-score, and when we subtract them, we'll find the area in the middle, which is our probability, which is what we're looking for. So back to my table, negative 0.4, and we're going to go to 6 up here. So negative 0.46 is 0.3228. And I can draw you another image if you want to see. 0.3228, and that is 0, and then we can find what one deviation is on this side. I'm looking for the positive 0.46, so I'm going to go the other table. Okay, 0.46 here gives us an area of 0.6772. 0.6772, and again, that's the area below the line that I'm drawing. So now if I subtract these two numbers, I can get the area without using any technology. Just doing it old school by hand, and we find that you have approximately 35% of the 35% chance that we will land within 0.05 of the mean. Okay, now Louise wants to be confident that his number is a true reflection of his local Good Burger. So he asked the group to collect data for a different 35 minutes. Now we have 140 minutes of data. He must have asked a couple of people to collect more data, and now we have a larger sample size of our local restaurant. We want to recalculate this and see if that gives us a closer probability of our mean falling within the mean of the population of Good Burgers. Okay, so what actual change do we need to make? The only change that we need to make is we need to change our standard error. So our new standard error of our sample size is 0.64 divided by the square root of 140 this time, which gives us 0.055 error. Notice that that is smaller than our original error. So we're using the central limit theorem here to say that if I use a bigger sample size, I'm getting closer to my mean. So that's what we're trying to show in this problem. So if I rerun these numbers, we find that Z1 is going to equal 2.65 minus 2.7 divided by 0.055, and Z2 is 2.75 minus 2.7 divided by 0.055. That gives us negative 0.924 and positive 0.924. Now I can go back to my table. And now I'm looking for 0.9 and positive 9. So there's 0.92 is 0.8212. And now this just looks like a crazy person is writing everywhere. Let me put that over here on our picture. And I'll find the other one, the negative version. Negative 9, 2 is 0.1788. And if I subtract those two differences, I will find the area between the two. It gives me 0.6424 or 64.2% chance. That is way better than my other one. So you can see that that larger sample size changed the answer tremendously. Okay, now let's take a look at the central limit theorem with proportions. With proportions, you can say that they are approximately normal, but they have to pass some assumptions. So they have to say that two assumptions here. The n is less than or equal to 5%, so no more than 5% of the population. This is going to ensure that we are independent. Wow. The sample size times the probability of success times the failure have to be greater than or equal to 10, and I can write that in for you. That's the sample size times the probability of success times the probability of failure. So if we're looking at a binomial distribution, we can still use the central limit theorem. As long as, when I multiply all of this together, we have a number that's greater than or equal to 10, and we can ensure independence of outcomes. So no more than 5% of the population can be in our sample. Okay. So when you're looking at the equations for this, we still have our mean is our probability of success. And then if you're looking at the standard error, it's still, or the standard deviation divided by the sample size. So it's P times Q divided by N, and then you can find the square root. So a lawyer estimates she wins 40% of her cases. So this is, she either wins or she loses. So we have two possible outcomes. So P, probability that she wins, is 40%. She currently represents 50 defendants. One second. Let X represent the number of wins out of 50 cases, so that P hat is equal to X over N, proportions of wins out of 50 cases. Use the central limit theorem to approximate the chance she wins at least 1/2 of her cases, or the probability that P hat is greater than 0.5. What's the probability that she wins at least 30 cases? Okay. So the first thing we need to do is check our assumptions. So our assumptions say that I can take the sample size, multiply it times P and times Q, and it should be bigger than 10. So I'm going to find Q really quickly. Remember, the probability of failure is 1 minus the probability of success, so that's 0.6. To check my assumptions, I need to multiply 0.4 times 50 times 0.6, and that gives me 12. So because 12 is greater than or equal to 10, I can continue. Okay. So my mu here is 0.4. And the standard deviation of the proportion is 0.4 times 0.6 divided by 50.